It's a pleasure for me to be here today. So originally I had planned to talk about my current research, but when I was asked to give the opening lecture, I felt it would make more sense to give a more general talk, and so I'm going to give a historical talk. So string theory has been described as 21st century science, which was discovered in the 20th century. Now, most of you are too young to have experienced what happened, so I think it might make sense for me to summarize some of the highlights and to reminisce about some of what happened in this opening lecture. Since I only have 25 minutes, this cannot be a comprehensive history, and so I will omit many topics, including two-dimensional conformal field theory, string field theory, topological string theory, string phenomenology, and contributions to pure mathematics. But even so, I probably have too many slides. So the subject of string theory emerged from the study of the strong interactions, and one of the approaches to the strong interactions that was pursued in the 1960s was an approach called S-matrix theory, in which one considered the S-matrix that describes hadronic scattering amplitudes by assuming some of their basic properties, unitarity and analyticity and angular momentum, and regipoles in the complex angular momentum plane. And a conjecture that was introduced by Chu and collaborators, the bootstrap conjecture, which developed into the concept of duality. Duality is used in many different ways. In those days it meant duality between exchanges of resonances in the S channel and the T channel. So the hope was that by implementing all of these properties, one could deduce or largely constrain the structure of the S matrix. A major breakthrough in this program occurred in 1968 when Gabriele Veneziano found an explicit realization of duality and Regge behavior in the narrow resonance approximation, and this was just given by Euler's beta function, where the argument alpha of S is the position of the leading Regge trajectory, and it's just a straight line as a function of the Mandelstam invariant S. Alpha 0 is referred to it as the Regge intercept, and alpha prime is the Regge slope. So the motivation for writing down this formula was purely phenomenological because it realized all of the principles that I discussed in the previous transparency. But incredibly, this phenomenological model turned out to be the tree amplitude for a full-fledged theory, namely a string theory. Very soon after Veneziano's formula, Virasoro proposed an alternative formula, which has 3 gamma functions in the numerator and 3 more in the denominator, which has similar virtues. Unlike the Veneziano formula, which had cyclic symmetry in the 4 external lines, this one has total symmetry. And soon thereafter, the n-particle generalization of Veneziano's formula was found. This was found simultaneously by several different collaborations. And the formula, which I've written on the slide, is the formula for the endpoint amplitude. And for a suitable measure function mu of y, this formula has cyclic symmetry in the n external lines. And then one can take linear combinations of these cyclically symmetrical amplitudes weighted with group theory coefficients that are referred to as Chan-Payton factors to give the full amplitude T. A similar formula was found by Joel Shapiro for generalizing Virasoro's formula, and this one, instead of involving real integrations, involves integrations over complex planes, z given by z. And this amplitude has total symmetry in the n external lines. Soon thereafter, Fubini and Veneziano showed that these formulas have a consistent factorization on a spectrum of single particle states described by an infinite number of harmonic oscillators, which are labeled by an index that goes from 1 to infinity, and another runs over the dimensions of space and time. which at this time was assumed to be four-dimensional. There is one set of such oscillators in the Veneziano case and two sets in the Shapiro-Virasoro case. Nambu, Nielsen, and Susskind independently interpreted the spectrum and amplitudes as the theory of a relativistic string. Open strings in the first case and closed strings in the second case. Having found the spectrum and tree amplitudes, it became possible to study radiative corrections given by loop amplitudes. And this started with the work of Kikawa, Sekita, and Virasoro. For lack of time, I'm being sketchy about who did what. However, I would like to emphasize the contributions of two people who passed away within the past year, Stanley Mandelstam and Yuichiro Nambu. Stanley Mandelstam joined Jeffrey Chew's nuclear democracy program in Berkeley in 1963. Its goal was that which I described earlier, to derive the hadronic S matrix from the analyticity, unitarity, and the bootstrap conjecture. I was a graduate student there in the heyday of this activity, from 1962 to 66. And Jeff and Stanley influenced my scientific development profoundly. So I feel very close to Stanley for that reason. Stanley introduced the variables ST and U that I used earlier, and derived what was known as the Mandelstam representation, which is a double dispersion relation in the STU plane. I suspect most of you have not heard of that before. Stanley made important contributions to Regé-Pol theory and proved the existence of branch points in the angular momentum plane. He proved the finiteness of n=4 super Yang-Mills theory, as well as the equivalence of the Sine-Gordon model and the massive Tiering model. Among his many contributions to string theory, Stanley obtained evidence for the UV finiteness of multi-loop string amplitudes, derived the fermion-fermion amplitude in the RNS model, and contributed to the construction of light cone gauge string field theory. So he would certainly be missed. The second gentleman, Yuichiro Nambu, was born in Japan, of course, where he worked with Tominaga and others. He came to the US in 1952. He spent a couple of years at the Institute for Advanced Study, after which he joined Fermi's powerhouse group, which included people such as Chu, Goldberger, Low, Lee, Yang, etc., at the University of Chicago. And he remained in Chicago for the rest of his career. Nambu contributed to a wide range of topics in physics. He received the Nobel Prize in Physics in 2008 for the concept of spontaneous symmetry breaking, which he developed while studying superconductivity. Even so, we know it's very important in particle physics and string theory. Nambu was an important early contributor to string theory in the years 1969 and 70. He was one of the first, perhaps the first, to recognize that the Veneziano model is actually the quantum theory of a string. And he introduced the elegant formula known as the Nambu-Goto action for the string. It is the area of the string world sheet multiplied by the string tension. And so in the formula shown, T is the string tension, and capital G is the induced metric in the world volume given by pulling back the space-time target space metric to the world G, as shown. So let me now tell you about the critical string theory. So in 1970, Gross, Neveu, Shirk, and I, as well as Fry and Susskind, studied one-loop amplitudes. Unexpected branch points that violate unitarity appeared in the non-planar open string loop amplitude. This was very disturbing. It seemed to undermine the consistency of the theory. In 1971, Claude Lovelace observed that these singularities become poles if the Regé intercept is 1 and the space-time dimension is 26. For these choices, the theory is perturbatively consistent, even though there are tachyons, of course. The new poles are interpreted as closed string particle modes. This was the discovery of open string, closed string duality. This discovery forced us to take dimensions greater than 4 seriously for the first time. It was literally on nobody's mind until this work of Lovelace. Since we knew about Kaluza and Klein, it should have motivated us to think about gravity, but that took a few more years. The critical string theory has an infinite set of gauge invariances that eliminate unphysical ghosts. These are encoded in the Virasoro algebra. Two different proofs of the no-ghost theorem were devised by Brouwer and Goddard and Thorne in 1972. In this case, only transverse excitations of the string give independent physical degrees of freedom, as was explained in an important paper by Goddard, Goldstone, Rebbe, and Thorne in 1973. In January of 1971, Pierre Ramond introduced a string theory analog of the Dirac equation. His proposal was that just as the string's momentum p mu is the zero mode of a string density capital P, the Dirac matrices gamma mu should be the zero modes of densities capital gamma. And then he introduced various Fourier modes of gamma dot p, as shown. In particular, the zero mode F0 is given by the Dirac operator gamma dot p plus terms that depend on various harmonic oscillators, bosonic and fermionic. Ramond then proposed the wave equation F0 plus m annihilates a wave function psi, and this deserves, in my view, to be called the Dirac-Ramond equation. Later it was realized that m should be zero. He also observed that the Virasoro algebra of the bosonic string generalizes to a super Virasoro algebra with odd elements Fn, that I showed earlier, and even elements Ln. This was one of the first superalgebras in the literature. It was infinite dimensional. A finite dimensional superalgebra was constructed by Goldfand and Lichtman, which namely the four-dimensional super Poincare algebra, and that appeared at just about the same time as Ramond's work, though its appearance was delayed by the Soviet authorities, so they probably did it earlier. A couple of months later, Neveu and I introduced a second interacting bosonic string theory, which we call the dual pion model. It has a similar structure to Ramond's theory, but the periodic density gamma of sigma is replaced by an anti-periodic one that we called h of sigma. Then the Fourier modes are labeled by half integers, and which we call G sub r. And these are the odd elements of a similar super Virasoro algebra to the one found by Ramond. Together with Charles Thorne, we showed that these bosons and Ramond's fermions combine into a unified interacting theory. Later in 1971, Gervais and Sekita observed that this string worldsheet theory is given just in terms of free bosons and free fermions in 2 dimensions, and that this action has 2-dimensional supersymmetry. And this, I believe, is the first supersymmetric theory to be identified as such in the literature. In 1976, this global supersymmetry and the super Virasoro constraints were shown to result from gauge fixing in action with local 2-dimensional supersymmetry. And this was done by Brink, DeVecchio, and Howe, and also by Deser and Zumino. This formulation was used by Polyakov in 1981 in his study of string theory path integrals. Now, string theory came on lean years after all of these successes. The reason was that as a theory of hadrons, it had problems. An unrealistic dimension of space, 25 or 9 space dimensions, and the presence of massless particles, which don't occur in the hadronic, it shouldn't occur in the hadronic spectrum. Moreover, the success of QCD made the effort to formulate a theory of hadrons based on strings less pressing. Also, there were other exciting developments at this time, including the completion and acceptance of the standard model, as well as grand unification. Understandably, quantum field theory regained respectability, and string theory rapidly fell out of favor. Despite this, some intrepid souls continued to pursue the subject, and one of them was Tamyaka Yoneya, who in 1974 interpreted the massless spin 2 state, or a symmetric tensor if you're in not in 4 dimensions, in the closed string spectrum as a graviton. Invoking a theorem of Weinberg, it was easy to show that string theory agrees with general relativity at low energies. Also, the massless spin 1 states in the open string spectrum could be interpreted as gauge fields, as had been shown several years earlier by Neveu and Shirk. In 1974, Shirk and I proposed to interpret string theory as a quantum theory of gravity, unified with the other forces rather than as a theory of hadrons. Once we decided to propose this, I knew what I would be doing for the rest of my career. This proposal had several obvious advantages. Gravity was required by the theory. String theory has no UV divergences. Extra dimensions can be a good thing in a theory where geometry is dynamical. Unification of gravity with forces described by Yang-Mills theories is automatic. Now, an important aspect of this whole story is supersymmetry and supergravity. Wes and Zumino, motivated by the Gervais-Sakita result that I mentioned earlier, pioneered supersymmetrical field theory in 1973-74. Subsequent works that are relevant to string theory include the discovery of n=1 4-dimensional supergravity in 1976 by Ferrara, Friedman, and van Nieuwenhuizen, and a slicker proof of it, supersymmetry, given by Deser and Zumino. 10-dimensional super Yang-Mills theory and n=4 4-dimensional super Yang-Mills theory were constructed in 1977 by Brink, Shirk, and me. 11-dimensional supergravity followed in 1978 in the work of Kremer, Julia, and Shirk, and n=8 d=4 supergravity the same year by Kremer and Julia. 2 years later, Freund and Rubin showed that ADS4 times S7 is a solution of 11-dimensional supergravity, one that is maximally supersymmetric. An SO8 gauged version of n = supergravity, which is important in ADS-CFT studies, was found in 1982 by DeWitt and Nicolai. In 1977, Liotzi, Shirk, and Olive proposed a projection of the RNS spectrum, both for the bosons and fermions, the so-called GSO projection, that removes roughly half of the states, including the tachyon. They showed that after the projection, the number of bosons and fermions is equal at every mass level. This was compelling evidence for the 10-dimensional space-time supersymmetry of the GSO projected theory, but it was not a proof. Also, it was not clear precisely what theories were possible. In 1979, Michael Green and I began a collaboration with the goal of understanding why the GSO projected RNS string theory has space-time supersymmetry. When possible, we also collaborated with Lars Brink. Our collaboration achieved the following. We formulated and named the Type 1, Type 2A, and Type 2B superstring theories. We developed a light cone gauge formalism for the GSO projected theory and used it to prove space-time supersymmetry of the spectrum and interactions. We used this formalism to compute various tree and one-loop amplitudes and elucidate their properties. And we formulated a superstring worldsheet theories with manifest 10-dimensional space-time supersymmetry and local kappa symmetry, which is a fermionic symmetry on the worldsheet. Anomalies played an important role in the story. In 1983, Alvarez, Gomez, and Witten derived the formulas for all the gauge and gravitational anomalies in any dimension and used them to exhibit miraculous cancellations in Type 2B superstring theory, proving that it could be a consistent quantum theory that violates parity. The Type 2B theory seemed unrealistic at the time since it does not contain any Yang-Mills gauge fields in flat 10-dimensional spacetime. But nowadays, non-perturbative vacua of the Type 2B superstring theory are considered promising candidates for realistic particle physics phenomenology. These studies go by the name of F-theory. Classically, type 1 superstring theory can have an orthogonal or a symplectic gauge group. In every case, a hexagon diagram appears to give a non-zero gauge anomaly, so it seemed unlikely that a type 1 superstring theory could give a consistent parity-violating quantum theory. However, in 1984, working at the Aspen Center for Physics, which I always like to advertise, Michael Green and I discovered that all gauge and gravitational anomalies can cancel for a theory with n equal 1 supersymmetry in 10-dimensional Minkowski spacetime, but only if the Yang-Mills gauge group is SO32 or E8 times E8. Within a few months of that result, Gross, Harvey, Martinek, and Rome introduced the heterotic string for the gauge group, which is more precisely described as spin 32 mod Z2 and E8 times E8. Shortly after that, Candelas, Horowitz, Strominger, and Witten introduced Calabi-Yau compactification. Applied to the E8 times E8 heterotic string theory, they showed that it could give four-dimensional effective theories with many realistic features. This got people really excited, and so after a decade in the shadows, superstring theory with the goal of unification suddenly became a mainstream activity. Also in 1984 was the discovery of T-duality. So the equivalence of circles of radius r and alpha prime over r appeared in a 1984 paper of Kikawa and Yamazaki. That was followed a couple years later by Narain's identification of the moduli space of toroidally compactified heterotic strings, which is given by the formula shown, and that involves a more general T-duality group by the discrete group that you see in the denominator. T-duality also relates the type 2a and type 2b theories in a similar manner. In 1996, Strominger, Yau, and Zaslow showed that mirror pairs of Calabi-Yau spaces have T3 fibrations, and mirror symmetry can be viewed as T-duality applied to those fibers. S-duality. Non-perturbative strong coupling, weak coupling duality was first proposed for gauge theory in 1977 by Montanen and Olive. In 1979, Osborne observed that the proposal was most plausible for n equal 4 super Yang-Mills. In 1990, Font, Ibanez, Lust, and Quevedo argued that T6 compactification of the heterotic string results in a non-perturbative SL2Z duality group in addition to the Narain perturbative duality group that I presented earlier. And they introduced the name S-duality for this duality group. And this can be viewed as a generalization of the Montanen-Olive conjecture in a context where gravity is present. In 1994, Ashok Sen produced non-trivial evidence to support the Montanen-Olive conjecture for n equal 4 gauge theories and string theories like the one I just mentioned. Following that, Vafa and Witten provided much additional evidence. In 1994 also, Hull and Townsend identified a similar SL2Z duality group for the type 2b superstring theory in 10-dimensional Minkowski spacetime. They also generalized this to discrete exceptional groups, which they called U-dualities because they combine S and T dualities. So that was the next letter in the alphabet. U-dualities for the type 2b theory compactified on a torus. In the middle years of the 1990s, 94 to 96, there was a burst of dramatic discoveries, and a period sometimes referred to as the second superstring revolution. This included, among other things, Seiberg-Witten theory for n equal 2 gauge theories, Seiberg duality relating various supersymmetric quantum field theories, the web of dualities relating various superstring theories, and M theory was discovered mostly by Edward Witten. D-branes and an appreciation of their properties and importance was presented by Joe Polchinski. Using D-branes and some of the other ideas I've described, Strominger and Waffe were able to reproduce the entropy of a black hole for an extremal black hole in 5 dimensions. And this was a major achievement. And F-theory, which I referred to earlier, was introduced by Waffe. Matrix theory is a proposal for a non-perturbative formulation of M-theory, and that was introduced by Banks, Fischler, Schenker, and Susskind. A year later, we have Maldaceno's dramatic result on ADS-CFT duality, followed by the works of Witten and Gupser, Klebanov, and Polyakov elaborating on the rules for how ADS-CFT works. Understanding ADS-CFT has kept us busy ever since its discovery, and so it really is 21st century science. So let me conclude. I'm pleased to see I reached the end of my transparencies before I was stopped. The history of string theory is one of unification, of particles and forces, of math and physics, and peoples and cultures. As you can see, we're gathered here from all over the world. So I'm proud and honored to have been part of this exciting adventure. I find it sobering to suppose that the final theory that we are dreaming of, to use the Weinberg's phraseology, has been and will be discovered many times in other parts of the universe, not to mention the multiverse. So thank you very much.